Schultz. So we're talking about chemical shift today in this presentation. Just want to make sure that's working here. So we'll start with the definition. Chemical shift is the difference between precessional frequencies of water and fat, and that has been measured to be 3.5 parts per million. Chemical shift artifact is the displacement of signal intensity due to this difference. So if we look at a fat and water molecule, we can talk about electron shielding first. Electron shielding, or the amount of protection a nucleus has from its electron cloud, affects the molecule's susceptibility to the external magnetic field, and this affects its precessional frequency. So looking at the two molecules on the left, we have water, that big bright red oxygen molecule. Oxygen is highly electronegative, and it attracts those hydrogen molecules to it, leaving the nucleus there more susceptible to the external magnetic field. Fat, on the other hand, has a huge electron cloud with all those white hydrogen balls on it, so its nucleus is less susceptible to the magnetic field. And how does that affect precessional frequency? Due to more shielding of the nucleus, fat molecules experience a weaker local magnetic field, and they will resonate at a lower frequency or spin more slowly than water. So when we put a patient in the magnet and we apply a gradient, that difference between fat and water at a 1.5 Tesla scanner is 220 hertz, and at 3T it's about 440 hertz. What is a familiar application where we can see this? Breast imaging is one. When we manually pre-scan our vibrant scan, we can see our fat and water peaks, and if we were to move between the two, we would see that they're 220 hertz apart. If there were silicone implanted in that patient, there would be another peak to the far right here, 90 hertz from fat. So this is also the basis for MR spectroscopy as well. There are two types of chemical shift. The first type is called mismapping artifact, and it's probably the one that we see most commonly as an artifact on our images. So it's most commonly seen around water-containing structures surrounded by fat, like the liver, kidneys, orbit, fecal sac. It occurs only in the frequency coding direction on spin echo sequences, and the artifact appears as a dark band on one side of the water-fat interface and a bright band on the other side. So if we imagine that this is our patient, and we're going to take a slice right through his abdomen where that red line is, this picture is sort of going to depict that slice. So if each white box here represents a pixel, we apply a gradient, we get a sample, we put that sample through Fourier transform, and we'll get a list of frequencies and a list of corresponding signal amplitudes for each area in that pixel. Let me get my pointer. So we can begin to draw in what we would expect to see in the water tissue here. We'd have some signal amplitude here, we'd have some here, and some in the fourth pixel. But when we move to the interface between fat and water, there's a shift, because although we would expect to see signal amplitude here, this whole system is based on the precessional frequency of water. And we need to remember that fat and water are 220 hertz apart. So instead of depositing signal here in this picture, this signal from fat shifts next door, and it's deposited here. And the same happens in this pixel. The signal from fat is shifted next door. And when we get to the third interface here of fat and water, this signal amplitude from fat shifts to the next pixel. And there's already inherent signal amplitude from the water that's currently there. So we have a surplus of signal here. It's the summation of the signal amplitude from the fat and the water. So on this side, we have a black signal void where signal is not deposited in our pixel. And over here, we have a surplus of signal causing a bright streak in our picture. this is an example of that. So axial T2 of the abdomen, the red arrows show that black signal void on one kidney, and the yellow arrows show that bright shift on the second kidney. What can fix this? To reduce this artifact, you need to increase your bandwidth. This will allow for a wider range of frequencies within a pixel and reduce the shift of signal intensity that is visible in the image. So if we went back here, this red arrow, I just picked an arbitrary number, 120 hertz. If that had been increased by increasing our bandwidth, the chemical shift would still occur, but it wouldn't be visible in our image because that shift would happen in the pixel. The second kind of chemical shift is called black boundary or India ink artifact. It's seen on gradient echo sequences and in and out of phase imaging, and occurs in both the phase and frequency directions. And this can be seen as a black line in all directions at fat and water interfaces. It occurs when a TE is selected in which fat and water spins are out of phase, canceling each other out. And we use this a lot in chest and abdominal imaging. So here are two gradient sequences, C-spine and knee, it looks like. So you can see the yellow arrows. There's a signal drop-off between muscle and fat, and that's that black boundary or India ink artifact. In and out of phase imaging occurs due to the difference in frequencies between fat and water. Their spins go in and out of phase with each other as a function of time. This period, called phase cycling, occurs every 4.4 milliseconds at 1.5 Tesla, and the cycle happens twice per 4.4 millisecond period. So because we know the difference in precessional frequencies of fat and water, we can select TEs to have spins that are in phase and out of phase with each other. So in phase, 4.4, 8.8, 13.2 milliseconds, and out of phase, 2.2, 6.6, and so on. This phase cancellation effect, or out of phase, can be used to quantify fat content in the liver and adrenal adenomas. Lesions whose signal intensity decreases when out of phase likely contain fat. So here's an example of that. It's a abdominal scan. On the left, in phase at 4.4 milliseconds, there's signal in that adrenal gland. Out of phase, that signal drops off because those fat and water spins have canceled each other out, and you have a loss of signal confirming that adenoma, that it is an adenoma containing fat. And to sum it all up, we can benefit from the effects of chemical shift and exploit these properties to help aid in diagnoses, like in the case of adrenal adenomas. However, when we decrease bandwidth or play with bandwidth, we need to be mindful of what this may do to our image. Although our intent is to increase signal to noise, we may inadvertently increase the artifact. In cases of high-resolution scanning, chemical shift artifacts can distort the borders between organs and between tissues. And that's it.
Perfect. Thank you. That is amazing. How long? I've been doing this for 11 years. This is the first time I hear India ink artifact. This is great. This is what makes our field so rewarding, right? Is every day you can learn something new, right? And then with every step we can become better and more knowledgeable and more able to